Hello dear students, hope you're all doing well. In this video, I will be talking about chapter 6, section 4, metallic bonding. Okay, let's start. What is metallic bonding? Guys, you remember in chapter 6, section 1, we talked about ionic bonding and covalent bonding. And in section 2, we talked about molecular compounds, their properties, their characteristics. In section 3, we talked about ionic compounds. In this section, I will be talking about metallic bonding, the bond between metal atoms. Okay? So what's metallic bonding? Guys, if you look at this, this piece of sodium, this is sodium, and you might ask what bond is between atoms of sodium metal. The bond between sodium metal atoms is metallic bonding. Okay, so how is this bond? Metallic bonding is attraction between positive metal ions and surrounding sea of electrons, electron C. So, what does it mean? Let's explain it. How does metallic bonding form in metals? How this happens? In metals, guys, empty orbitals at the highest energy levels overlap. What does it mean? Guys, metal atoms, they have empty orbitals, okay, in their last shell. So in their last shell, there are empty like rooms. They do not contain any electrons. Example, sodium. Look at sodium. This is orbital notation of sodium. Sodium, it has one valence electron in the last shell, in the third shell. It's in 3s orbital, but you know in the third energy level, instead of 3s we have 3p also. Basha. But 3p orbitals, they're empty. These rooms, they do not contain any electrons. Basha. In metals like sodium atoms, these empty orbitals, they overlap. And this is a sodium atom, Basha. This is a sodium atom. There are millions of sodium atom in a piece of sodium metal. Okay? So these empty orbitals, imagine we have another sodium atom next to this sodium, Basha. Also they have what? There are empty orbitals too. 1, 2, 3. We have another sodium also. These empty orbitals, they bind together. It's like that. They join together. We call overlapping. Basha, these, they overlap. Basha, this is between two sodium, but it happens between millions of sodium atom. It will be like a network of empty orbitals. They have overlapped. What happens to the valence electrons of sodium atoms when their empty orbitals overlap? These sodium, we have another also electron here. These empty these electrons, the valence electrons of atoms, each sodium atom, its valence electron moves throughout these empty orbitals. Okay? Means that we can say sodium atoms, they lose their electrons to where? To the empty orbitals. Okay? And the electrons, they like move freely throughout these empty orbitals. Okay? 3p empty orbitals. Now we can say sodium atoms, they become positive. They become cation, isn't it? Because their last electron, their valence electron, it has become delocalized. What does mean delocalized? Means that the the electrons, they do not belong to any atom. Okay, look at here, guys. Imagine this sodium atom. Sodium atom, it has one valence electron. These two sodium atoms, their orbitals, their 3p empty orbitals, they have overlapped. It means that these two sodium atoms, they have overlapped. They have bind together. So now, when they bind together, when their empty orbitals overlap, the electrons, they move from one atom to another atom throughout the empty orbitals because their empty orbitals overlap. So this electron comes here. At the same time, these two atoms, their 3p orbitals, they have overlapped because it means that these two atoms, they have like connected together. So the electron comes here also. Also it comes here. It will be like these electrons, they become free throughout the entire metal. This electron moves from one end to another end of the metal. Means the electrons, they are free. They are delocalized. Delocalized. What does mean delocalized? Means they do not belong to any one atom but move freely throughout the metal's network of empty atomic orbitals. What are the empty orbitals here? For example, for sodium is the 3p empty orbitals, but in D block also we have 3p, for as we have 3D, for example. Also they have empty orbitals in 4p, they move there. So here we talk about sodium atom. So what's the metallic bonding now? Metallic bond is between these free electrons and positive metal ions. Why positive metal ions? We said the metals, they lose their electrons to the empty orbitals, and the empty orbitals, and where the electrons, they move, is called electron-C. So we say the attraction between positive metals, because we can say they lose their electrons to the electron-C. So the attraction between positive metal ions and surrounding sea of electrons, okay, between the free electrons and sodium metals, is called metallic bonding. Look at here, imagine this is a piece of sodium. It has one valence electron. These valence electrons, they move throughout the entire metal, each one. So the attraction between these free electrons and metal atoms now they're positive. Why? Because they have lost their electrons to the electron-C, okay, to the empty orbitals. Okay, this is called metallic bonding, attraction between positive metals and the electron-C, free electrons. Basha, let's talk about the structure, how the metal atoms, they're packed together, okay? Metal atoms are packed together in a crystal lattice. I think this word is not new for you. We talked about ionic compound. We said the positive and negative ions, they are arranged in a crystal lattice that makes the ions, okay, positive and negative ions, their potential energy be decreased to become more stable. So also metals, they're packed together in a crystal lattice. So it's like a crystal. Imagine, look at here, a crystal structure of sodium. Look, each sodium atom is surrounded by 8 other sodium atoms. Okay, here this is 1, 2, 3, 4, 5, okay, 6, 7, and 8. This is the crystal lattice of sodium. but it's not same for all. Not each metal atom is surrounded by other 8 metal atoms. This is for sodium. For other metals it might change. Okay. Metallic properties. Metallic bonding gives metals some properties. One of them, a good electrical conductor. Metals, they are good electrical conductor. Why? Because of its valence electrons are delocalized. You know, we said delocalized means the electrons, they move freely throughout the entire metal. They do not belong to any metal. They move freely throughout the empty orbitals. So when the electrons, they are delocalized, they move from one end of the metal to other end of the metal. Therefore, the electrons can move from one end of the metal to another end. Means electrons, they're free. So now they can carry currents. Okay, electrical currents. So high luster. Why they reflect light? Why metals, they're shiny? Look at here. Look, why they're shiny? Why they have high luster property? Because metals, they contain orbitals. These orbitals, they are separated by extremely small energy differences. And the orbitals of metals, the difference in their energy is very small, extremely small. So this causes metals to absorb wide range of light frequencies. So means they can absorb high amount of light. Okay, wide range of light frequencies. This absorption, so now metals, they can absorb high amount of light. What happens when metals, what happens to the metal atoms when they absorb high amount of light? This absorption of light results in excitation of metal atoms' electrons to high energy levels. Do you remember in chapter 4, section 1, we talked about we have absorption emission. When an atom absorbs light, their electrons, they move to high energy level, right? This is called absorption. So also here in metals, their electrons, they move from one level to another level, energy levels, okay? This is, they jump to high energy level because when they absorb energy, their energy level will be higher, and they move to high energy level because they have high amount of energy now. But we know that electrons, they do not stay in the high energy level. They fall back, they emit the light, they have what? Absorbed. Here it's written, in metals, electrons immediately fall back down to low level, emitting energy in the form of light at a frequency similar to the absorbed frequency. Means the amount of light they absorb is equal, the amount of light they release throughout the emission, it equals to the amount of energy they absorb. Look, atoms, metal atoms, they absorb light, high amount of light. Their electrons, they jump to high energy level. They fall back, they emit the light they have absorbed. That's why the light they reflect is the light you see. The light you see is the light of the electrons. They fall back to lower energy level and they emit the light. Okay. Another property, malleability, is the ability of substance to be hammered, beaten into thin sheets. We learned that metals in chapter 1 we learn we can hammer, you can bend and make different sheets from metals because they have this property which is called malleability without breaking any bonds. Metals you can bend, you can make thinner. Okay, So ductility, ductile, is the ability of substance to be drawn. You can draw, you can pull, okay, without breaking. Okay, here copper metal, you can make copperware, you can pull it. So these two properties, guys, allow metals to be formed into hard structures. That's why metals, they are hard structures, because they have malleability and ductility properties. Okay, why metals are malleable, ductile, but ionic compounds are not? Or we can say why ionic compounds, they are, you know, ionic compounds like salt, okay, salts generally they are ionic compounds. So why they are brittle, you can break easily. So sea salt, actually it's big in size, you can easily break. But metals, like a piece of iron, can you break easily? No. Why? Look, is uh, metallic bonding is uniform throughout the solid metals, and one group of atoms can slide past another group without in the electron sea without breaking any attraction. Look, in metals, okay, one group of atoms can slide past another without any bond breaks because they have malleability and ductility property. So the bond between electron C and metals does not break. Okay, but what about ionic crystals? Ionic crystals, like ionic compounds, they are held together. We know in ionic compounds there are positive negatives. Look at here, this is an ionic crystals. The negative positive ions, they are extremely, there's a strong attraction between them. Okay, but if you try to move one plane, one side, okay, one part of sodium, and if you try to break it, okay, what happens if you try to force a side? The like charges, look, guys, moving one plane of ions causes ions with the same charge to become lined up together, resulting in the splitting of the lattice. Guys, look, this is, imagine a piece of ionic compounds. You have forced a plane. What happens? The like charges, they become lined up together. So negative negative. Normally it's not like that. You have a negative positive positive negative, so they have not lined up together. But when you force a side, a plane, so the like charge, they line up together. So we know like charges, negative negative positive positive, they repel each other. When they repel each other, this repulsion causes the ionic crystal to split. Okay, like charges repel each other, thereby splitting the lattice. Okay, that's it. That's why ionic compounds, they're brittle, because when you move a plane, when you force a side, like charge, they line up together, then they repel each other, it splits, it breaks the crystal lattice. Okay, metallic bond strengths. Guys, how we know how strong is a metallic bond? Because a metallic bond is not same between all metal atoms. Okay, all different types of metal atoms. It changes. How it changes? Let's talk about it. Factors affect the strength of metallic bonding. So first, number of valence electrons. If there are more electrons in the electron sea, you know where electron sea, free electrons, okay, we call them electron sea. So the more electrons in the electron sea, the place that where electrons they move, the stronger metallic bond. Look how it happens. Look, this is sodium, magnesium, aluminium. Sodium, it's in group 1, it has one valence electron, right? Each sodium, it has one valence electron. Basha. Magnesium, it's in group 2. Each one of them, it has 2 valence electrons. Aluminium, it's in group 13. It has 3 valence electrons. It's metal. Basha. So what happens when there are more electrons around these positive metals? The number of attractions increase. So imagine this is a positive. There are 3 electrons. Basha, for aluminium. Okay? When there are more attraction, right? There will be stronger attraction between metals. But if we have one sodium, like 1 electron, so the attraction, so look, there are 3 electrons in aluminium. They like attract to the sodium, to the aluminium metal. So when there are more electrons, more attraction, stronger is the metallic bond. Okay? Another is atomic radius. The smaller the atoms of a metal, stronger will be the metallic bond due to greater force of attraction. How? Look, we know that when size increase, what happens when size increase? So imagine this is lithium, Asha. Lithium in metals, they lose, like they lose their electrons. Lithium, and we have sodium, but sodium, it has it has 3 shells. Basha, it has 3 shells, they contain electrons. So when the size increases, the nucleus of atoms, and the distance between nucleus of the atom to the sea of electrons increases. The distance increase. This is sodium. So, but lithium, the distance between lithium atom and the free valence electrons, right? Because valence electrons, they become delocalized. That's why I have not written on this line. So the distance is more. Here in lithium, distance is shorter. When the distance is shorter, the free electrons and sodium and nucleus distance is shorter. So when the electrons and protons, they are closer to each other, so the stronger is attraction. We learned that when a negative and positive, they're close to each other, the stronger is the attraction. But for example, the electrons, they are a little bit farther from the nucleus and weaker is attraction. So if we say that is the attraction between lithium atoms, is it stronger than the attraction between sodium atoms? Lithium atoms, they're stronger than sodium atoms? We say yes, because lithium's size is smaller than the sodium size. Okay, that's it. But how can we measure the strength of metallic bonding? We know these factors, they affect any number of valence electron, atomic radius, they affect the strength of metallic bonding. We know number of electrons increase, Basha, metallic bond strength increase. Atomic radius decreases, means those metals, their atoms size is small, means there is a strong metallic bond between the atoms. Okay, so the strength of bonds that hold the metals together is measured by amount of energy in the form of heat required to vaporize the metal. This is called enthalpy vaporization. Guys, we to know how strong is the metal, we must measure it. How we measure it? We measure it by the enthalpy vaporization, which is that the amount of heat a specific amount of a metal absorb to vaporize, to become gas. If a metal needs more heat, and if it absorbs more heat to become vapor, means there is a strong attraction between the atoms, metal atoms, okay? So here, for lithium, the enthalpy vaporization of some metals, lithium, which is in second period, its enthalpy vaporization is 147 kilojoule per mole, but beryllium 297 kilojoule per mole. Means beryllium's enthalpy vaporization is higher than lithium. Means beryllium absorbs high amount of energy to become vaporized. Okay, why? Because we know across the period, lithium it's in group 1, beryllium it's in group 2, but the second period. Across the period, what happens? Size decreases. Size of beryllium atoms smaller than the lithium atoms. So when the size decrease, what happens? Metallic bond strength increase. So there's another factor. Across the period, lithium has 1 valence electron, beryllium has 2 valence electron. So when there are more electrons in the electron sea, is stronger the attraction. As I explained it, there are more attraction between electrons and metal atoms. So in beryllium also is like that. Beryllium has 2 valence electrons. Lithium atoms, they have 1 valence electron. So more electrons in the electron sea, stronger is the metallic bond. But if we compare lithium with sodium, sodium's enthalpy vaporization is 97. It needs 97 kilojoule per mole to sodium change to gas, to vaporize, okay? While lithium's enthalpy vaporization is more than sodium. This because sodium's size is more than lithium size, okay? So when the size increase, we know electrons, distance between C of electrons and sodium metals nuclei increases. Size increase, distance increase between electrons and protons. At this time, the attraction decreases. Attraction decreases means metallic bond strength decreases. Okay, potassium size is more than sodium. So the electron C, distance between electron C and the nuclei, what? Increases. So strength of metallic bond decreases. Okay, that's it. But look, in the same group, valence electrons down the group does not increase. So why metallic bond strength decrease? Because size increases. Okay, that's it. This is how we measure the enthalpy, how we measure the strength of metallic bonding. Okay, this is section review and answers. Inshallah, next video I will be talking about chapter 6 section 5 molecular geometry. Okay, see you.